here are a couple more closely related examples to the series that we just looked at. And so here, let's say that we're looking at e to the minus n times n to the 3.2. So between this one and the previous example, there are just minus signs added to both of the powers here. And so now the point is that this exponential e to the minus n is going to 0 really quickly, and the polynomial is going to infinity relatively slowly. So the intuition here is sort of the opposite of last time, which is that n to the 3.2 over e to the n approaches 0 very quickly. And so that means that it should converge. All right, and so now we need a formal test in order to show that this is true. And so first of all, the nth term test is not helpful, again, because the terms do go to 0. And so it's never helpful in that case. The direct comparison test probably is helpful here, and that's because we have a compound leading term, and by that I mean a product of two functions, and we know which one dominates. And so this is which part of the leading term dominates. I forgot the word of, so I'll add that in. There we go. Okay, and then the limit comparison test is sort of iffy for this one because we already have the clear leading term. It just happens to be a compound one. And so it would be more difficult to use the limit comparison test here, although we could use it. And so maybe we'll look at how that would look in a minute. And the integral test, again, here is not very helpful. And the reason for that is similar to last time, which is that x to the 3.2 divided by e to the minus x is not easy to integrate. And so this is not really a test I want to consider here. All right, so let's look then at the direct comparison test and see how we would apply it here. And so we know at this point that we want to show that this series converges. And so that means that we would want to find something bigger than it that also converges. And so in this case, n to the 3.2 over e to the n, first of all, that's certainly greater than or equal to 0. And now I need to find something that is less than or equal to. And so the point here is that we know that n to the 3.2 is always going to be less than any exponential as long as the base of that exponential is greater than 1. And so we could choose anything here, like e minus 1, for example, to replace that, to the n over e to the n. And so this is true, again, because exponentials are bigger than polynomials. And so the reason why I wanted to pick e minus 1 is because I know that e is 2.7 something. And so e minus 1 is still greater than 1, but it's also less than e. And so I definitely want to choose something here that's less than what's here. And so that just seemed like a convenient choice. It's certainly not the only choice, but it's just one option that would work there as a direct comparison. Okay, and so once we have this, I can combine everything into one power. And so that'll be an e minus 1 over e raised to the n. And now if I simplify this by breaking up the numerator into two different fractions, then I'll get that this is 1 minus 1 over e to the n. And so now we know that the sum of 1 minus 1 over e to the n, that converges because it's geometric, with r being equal to 1 minus 1 over e, which is less than 1 because I'm just subtracting something from 1. And so that means that our original series, the e to the minus n to the 3.2, converges by direct comparison because it's smaller. Okay, so I should mention that one thing about this is a little bit wishy-washy, which is the inequality that I said right here, because I sort of said this intuitively by saying that polynomials are less than exponentials in the long run. So this inequality might not actually be true for every value of n, but I don't care about that because the point is that it's true for all n that are large enough. And that's all I need in order to compare series. In other words, the only part of a series that determines whether it's infinity or not is the last part of the series. The first few terms in a series, the first million terms, the first 10 million terms, they don't make an impact as to whether or not the series is infinity or not. Okay, let's look at the next one. So here we have 3 plus minus 1 to the n over n squared. And so this term right here is going to be annoying because it oscillates between a plus or a minus 1, and it doesn't have a limit as n goes to infinity. However, it's going to be negligibly small in comparison to the n squared in the denominator. And so it's also the case that this particular oscillation is not going to affect whether or not the numerator is positive or negative because the 3 is already bigger than a minus 1. And so that means that my intuition is that this is going to be roughly like 2 over n squared, which is sort of what would happen if you subtracted a 1 from the numerator, or maybe 4 over n squared, which is what would happen if you'd add that 1 to the numerator instead, and both converge. And so that means that it does too. All right, and so again, I need to be able to show this more formally. And so for the nth term test, that's not going to be helpful here, again, because the terms do go to 0. The direct comparison test is going to be helpful, and that's because I can replace the minus 1 to the n with either a plus or minus 1 to find upper bounds. And so in other words, these oscillations are always going to be good candidates for the direct comparison test. And that's just because we can remove them by making a nice comparison. The limit comparison test is probably not helpful here. And the reason for that is because the minus 1 to the n is roughly the same size as another constant, or in other words, the 3 in the numerator of this series. And so that means that there's not a clear leading term in the numerator here, because they're both roughly the same size, because they're both constants. And so you maybe could do something fancy with the limit comparison test, but it would be more complicated, and it's easier to use a direct comparison here. And then again, the integral test, still not easy here, because 3 plus minus 1 to the x over x squared, that's not even a function that makes sense, because if I take minus 1 to the 0.5, it's not clear what I mean. And so there's no way I can even talk about the integral here. Okay, so now let's look at what the direct comparison test would tell me here. Again, I know that my goal is to show that this does converge, which means that I want to find something bigger than it that also converges. And so in this case, I will find the upper bound of 4 here. And then this last part here, this converges by the p-test. So the sum of 4 over n squared converges by the p-test. And that's because p is equal, sorry about that, p is equal to 2 here, which is greater than 1. And so that'll mean that it does converge. And so then by the direct comparison, this original sum converges as well.